it out when I get to the end. I haven't recorded anything, but I gotta turn this in, so. Okay, my name is Joli. I feel like I'm giving a talk in church. I've been asked to speak on the periodic trends lecture. I believe it was lecture 10 if you want to go back and look. But basically, periodic trends are specific patterns that are on the periodic table that we see every day. And so they illustrate different types of elements, the aspects of certain elements, including like size and electronic properties. Um, the main periodic trends that we're going to cover today are electronegativity, ionization energy, electron affinity, atomic radius, and yeah, I think that's it. Um, they're important. I think it's helpful to know like why things are important, and they're important because they help us predict an element's properties like melting point, boiling point, electronegativity, how stable they are, etc., etc. Um, and they exist because of the atomic structure of each element within their group, within the periods, and just because of the way they are. So let's get started. Why isn't this working? Okay, I think it's still working. Sorry, 1 second. I don't want to capture. Okay, so the learning objectives that they want us to know for this are that we can use the periodic table to determine these trends, atomic size, ionic sizes, ionization energy, and electron affinity. I think I said electronegativity, but I don't know if we're gonna talk about that. I don't think so. So yeah. Also, if you hear my mom talking in the background, please ignore her. She just talks really loud when she talks on the phone. Okay. So we're gonna first talk about the periodic table because it's helpful to refresh on what exactly everything is. So over here on the left, we got our metals, and those are usually shiny solids. They usually conduct heat and electricity, and they're usually malleable or ductile, whatever that means. We usually can like move them, and they usually lose an electron to form cations, um, which means that it's more positive. It's got a positive charge, because they want to try to get over to, yeah, they want to try to just lose that because it's closer to the noble gases. Um, then you have nonmetals that are here in red, no, that are in green, sorry. And those can be solids, liquids, and gases, and they're not very good conductors, and they usually gain electrons to form anions. Metalloids are here in the blue, kind of a bad drawing, but they're usually shiny like metal and they're brittle like non-metal, so they'll like break easily and they're kind of semiconductors. So the periodic table organizes all these elements according to similar properties. So you can just tell, so you can, like the point of these trends is to be able to tell, well, the periodic table actually, is to be able to tell the characteristics of each element, according to groups and families, just by looking at the periodic table. So here are the families. Here are alkali metals, alkali earth metals, and then we have transition metals in the middle. We've got non-metals, noble gases that have 8 electrons, don't want to gain any or lose any. Then we've got halogens. What's the green? Not really sure. We'll figure it out later. Okay. So if we remember, it's important to remember like our electron configurations, S1, S2, etc. Because those are reflected on the periodic table. It's important to recognize energy levels by period, 1, 2, 3, 4, 5, 6, 7, as you go down. I think I can show you. I don't know if you can see my mouse. That's important. And then the columns, they all have like the similar chemical reactivity. So if we kind of remember that, it'll help you in understanding periodic trends. Okay, we're going to talk about Z, F, and Z effective. So here's like one more formal explanation, and then I'll kind of give you like what I feel like helps me understand it best. Most of the physical and chemical properties of the elements can be explained on the basis of electron configuration, so we were just talking about. And so if we consider the behavior of ionization energies in the periodic table, it is known that the magnitude of the ionization, so it's talking about like the energy, potential depends upon the following factors. So ZF and Z effective are affected by these things: the size of the atom, the nuclear charge, the screening effect of the inner shells, and the extent to which the outermost electron penetrates into the charge cloud set up by the inner lying electron. Okay, so to break that down, this is how I make sense of it, and this is what I posted here. Z is the overall charge of the nucleus. That's like what's coming from all these positive charges in the middle. Z effective is when a valence electron is further away from the nucleus and it experiences a change in energy, a decrease in energy, based on these things that I was talking about: the size, the nuclear charge, and the screening, and how close that electron is to the cloud. Most often, it's experiencing electron shielding, where other electrons located between the valence electrons decrease the overall nuclear charge. So, like, if you have a ton of electrons swimming around, they're going to decrease the overall charge because electrons on the outside can't get to the energy that's going from the inside, and they cancel each other out. So, in other words, Z effective is a portion of the nuclear charge that the electrons actually experience. So, we got all this good stuff, all this charge in here, but because there's some shielding going on, because it's far away from the nucleus, or because, there's a ton of electrons in the middle, this electron isn't getting as much, and it's experiencing Z effective. So, just like defective, kind of. Not sure why it's called effective, but it's okay. Okay, moving on. So basically, the further away electrons are, and the more there are of them, the lower the nuclear charge. The ability of the nucleus to bind electrons depends on the charge of the atom and the number of protons that we have. How am I doing on time? Okay, we're good. So we're going to look at these trends today. These trends help us understand the periodic table, and it depends on the electron cloud and how it involves the electrons individually and how strong the electrons are bound to the atom. So that's gonna, I don't know, that really helps me understand what these trends are, as we think about the cloud and we think about how strong the electrons are bound to the atom, and that depends on energy, affinity, radius, and yeah, that's what's gonna happen. So yeah, just like you can take a look at this one here. Yeah, whatever. Okay. The first one is atomic size. So atomic size decreases across the period because as you go across the period, your protons are increasing, right? But the more protons you have, the higher Z you have, and that's going to bring your electrons out. It's going to be have a stronger bond between the nucleus and the electrons. I'm not sure if that makes sense, but basically, the more protons you have, the higher Z you have. That's going to decrease the size because they're going to pull everything in tighter. And so, even though you have elements on the same energy level, they still decrease in size because they're increasing in protons and they have a stronger charge. And not sure why transition metals don't really change. Probably should know that, but I don't. But yeah, let's move on. So cation and anion size are important because they help us to understand like how big an atom will be if it loses or gains an electron. So a cation has fewer electrons, right? Because it's losing an electron and it has a positive charge. So there are the same number of protons, but there are less electrons, and so it's going to be tighter. Like kind of like we saw in the last one, it's going to have more energy and pull everything in closer. Um, the anions are the opposite. So you're going to add electrons, it's going to be bigger, and there's going to be more electron shielding, and everything's going to cloud. There's not going to be as strong of a bond, and there's just going to be more to accommodate for. So I wrote here in small just because I did. But the way I think about it is that, like in families with less kids where their parents can give them more attention, like maybe the family's tighter because the parents can give them more attention, they have a better relationship. And then if you have like a family with like 12 kids, it's hard to have the same relationship with each kid and have a really tight bond. I don't think that's true. I don't mean, I don't know. I'm an only kid, but yeah, that's just the way I think of it with cation and anion sizes and all of the atomic sizes essentially. Ionization energy is the amount of energy it takes to remove an electron from its shell. So I'm going to read a little bit of the formal explanation. Um, Ionization energy is the energy required to remove an electron from a gaseous atom or ion. The first or initial ionization energy of an atom or molecule is the energy required to remove 1 mole of electrons from 1 mole of isolated gas atoms or gas. You may think of energy as a measure of the difficulty of removing electron or strength by which an electron is bound. The higher the ionization energy, the more difficult it is to remove an electron. So I put it right here. Yeah, so it increases across the periodic table, from left to right and um, from bottom to up. Sorry, I just had a brain lapse. Um, and that is because we have, the bonds are tighter and it's harder to remove them and they're closer to the center of the nucleus. And so basically ionization energy is like how much energy it's going to take to remove it from that tight bond. Um, Ionization energy is always reported in kilojoules, and it shouldn't be confused with like delta H or anything like that. Energy generally increases moving from left to right, like it said. And this is because the atomic radius, like we see here, is decreasing, so there's greater attraction. Um, and the ionization is at minimum value for the alkali metals on this side. And so because it doesn't have very much ionization energy and it really needs to take away their electron. Like I said earlier, it's more favorable to take off an electron for the alkali metals, so their ionization energy is really small. And on the opposite, the ionization energy for the noble gases is really large because they already have 8 valence electrons and they don't want to take any off. So you're going to have a tighter bond and it's going to be harder to remove them. Okay, so here's some anomalies when it comes to the trends. Half-filled p subshells of group 15 elements is particularly stable. So let's look at that. P subshells of group 15. What's group 15? I think that's like 17, 16, 15. Okay, so these subshells are really stable. So they it takes more energy to remove an electron, so more ionization energy to remove an electron than the other electrons. And then in group 16, for some reason, oh, I got out of that. They want to be half filled, and so they lose an electron instead of gaining a couple. So ionization energy is less for group 16 than it is for 15 because these ones don't want to lose one and these ones do want to lose one. So this ionization energy is less. Okay. Okay. Yeah, so if we look at our periodic table, let's look back. Even though the trend goes from left to right on ionization energy, it's actually going to be opposite right here. It's going to take less energy to remove an electron from O than it is going to remove an electron from N, if that makes sense. It makes sense to me because I made this. So the last one we're going to talk about is electron affinity. Electron affinity of an atom or molecule is defined as the amount of energy released when an electron is attached to a neutral atom or molecule in the gaseous state to form a negative ion. So it's the energy change when it gains an electron to form an anion or a negative anion. Basically, so I said the last shouldn't be confused with delta H when I was thinking it was electron affinity shouldn't be confused with delta H. So ionization energy is talking about like how difficult it would be to remove an electron. Now electron affinity is talking about how much energy it releases when it removes one. So just remember that it's not the same as enthalpy of ionization. But we know that when an electron is added to a neutral atom, the first electron, the energy is released. And the first electron affinities are negative. However, if energy is required to add an electron to a negative ion, like a second electron affinity, I don't know if that makes sense. It doesn't super make sense to me, which overwhelms any of released energy from electron attachment process. Second electron affinities are positive. So if you take an electron away and it leaves a negative ion, it's negative. The electron affinity is negative. But if you take it away again from that negative ion, it's going to be positive. Anyways, that was a lot more explanation than is needed to really understand this trend, at least in my opinion. But what we really need to know is that electron affinity increases, it gets more negative, which means it doesn't want an electron. So kind of similar to ionization energy, all these electrons, it's like these are groups. These are groups of girls. I think RTA talked about how like having more electrons is like having more girls, and it's easier to talk to just one girl than just like a group of girls. So the more you have electrons you have on the side, the harder it is to add an electron. Like we said, noble gases is a good example. They have eight valence electrons. They don't want to add one. And you have the ones over here. They like to add one because, yeah, I think I said that wrong. Sorry. Electron affinity is more negative as you go up, so it wants more electrons. I think this one wants to lose electrons. That doesn't really make sense. But just remember that electron affinity increases as you go to the right, and it increases as you go if you go from downward to upward. And what's confusing about that is that when it says it increases, it says that electron affinity is more negative. So it wants to add an electron more, but we're still saying it increases. So yeah, okay, I think that's a little bit messy of an explanation. I'm sorry, I apologize. But yeah, if you just remember the trend for this, you're golden. And if you understand all of these other things, that will help you. So I put together a few practice questions that like helped me like understanding the difference and just understanding the melting points. Yeah, I don't have very much time, so I'm not gonna go over each one, but I included, if you want to take a screenshot of this or pause the recording and like write down your answers, I included all the answers right here. I think this up here should not be there, but yeah, that's all I have to say. I would say contact me for more information, but I'm just a student and I probably can't give you the correct information. Here is another picture of the periodic trends. If you want to screenshot that and to study, I personally think that this is one of the easier lessons. So maybe go study the math ones. But yeah, thanks everyone for tuning in and good night.